Hi all. In this video, I would like to talk about first order system responses. In our previous videos, we talked about what the system order is, and we learned how we can go from differential equations to transfer functions. The mean is going from the Laplace domain, the S domain, to time domain, and the inverse manner. And today, we will kind of combine those two topics together and we will take a look at responses. So let's write down our topic: first order system response. This is a beginner but a vital topic for control engineering students, because it's the first step on analyzing the responses of some systems. So first of all, let's repeat what we learned in the previous courses so quick. So first of all, we define some GS or HS, whatever you call it. Then we call this the transfer function, right? This is our transfer function. And this function was consisting of two separated parts. The first was CS, and at the bottom we have RS. And CS stands for the output function, and RS stands for the input function. That was easy. And if you get to ask about response, you should find out and you should work in terms of the output, because output is how our system responds, right? So if I get to tell you, leave the output alone, what you're going to do is you will just take this RS onto the left hand side and let CS alone. So this is the responses equation. Input times the transfer function. So if you get asked to find response or draw the response or any other thing like finding a response, you should do this and let CS alone. So let me draw you a typical, most widely used first order system. So let's say we have an HS, which is, let's say, A over S plus A. Why is this a first order transfer function? Because in the denominator part, there is only S, which has a power of 1, S to the power of 1, and there is nothing more. So it is a first order transfer function. And usually for first order transfer functions, in the questions or in exams, you probably get asked to find the response of this first order transfer function to unit step. And unit step is 1 over S in S domain. We learned this in previous courses. So what we will do is actually, let's say CS equals RS times HS. No need to write it, but I will write. This is RS, unit step. It's our input. So we will do 1 over S times A over S plus A. That's simple. But if it's wanted from you to find the response, we should go to time domain, because we will analyze the system in terms of time, how the system behaves throughout time, reaches out to infinity or reaches out to a certain value. So if we want to get to the time domain, the t, we should do inverse Laplace. And to do inverse Laplace, we had some kind of equations which are too easy to convert into inverse Laplace. We need to break these parentheses into two different separated parentheses. So I will write it down with this red marker. We will apply this method, partial fraction expansion. So let me just directly do it so that you will understand it better. So I encircle this equation with this blue mark, and I will continue it on below. So let's say A over S plus B over S plus A equals our CS, which was A over S times S plus A. And I say, let's equate the denominators so that in the numerator part, I will have the same coefficients or same numbers. So let's do it. I just equate all the denominators and I will have A times S plus A plus b times s equals to a, right? So let's find out a and b separately. So we have, let's write down s equals to 0, the b part is gone, and I can say a times s is lowercase a. So I can say a is, let's say 1. I mean, this s is, sorry, this is a, because we had s0, a times a is 1. With a similar manner, let's say s equals to minus a, because I wanted to get rid of this a part, and then I will see here minus b times a equals a. So I can say b is minus 1. So at the end of the day, let's go back to black marker. So I can say a is 1, so 1 over s plus, minus, since we found b minus 1, minus 1 over s plus 1 is my, s plus a is my final CS. And it is so easy now to convert it into inverse Laplace to time domain. 1 over s in time domain is 1 minus, if we have an expression like 1 over, or a value over s plus a value, it is kind of similar with like this exponential function. So I can say it is e to the power of minus at, right? So this is my CT, guys. Okay. And you found your response function in the domain of time. So I can analyze, I can see how the system behaves. By the way, guys, don't forget, we mentioned this before, but I want to mention it again. This constant part corresponds to our forced response because it's the part of the input, and this part is our natural response because at the end of the day it will reach out to 0. Yep. Okay, let's move on with blue marker. So we have this 1 minus e to the power of minus at. Okay, so I need to see how this system behaves or acts throughout a certain time. So if I get to say t equals 1 over a, let's try out what happens. If I put 1 over a instead of t, I will have 1 minus e to the power of minus a times 1 over a, which is minus 1. So I will have 1 minus e to the power of minus 1, which I already written here. E to the power of minus 1 is 0.37. So at the point of 1 over a, my system is at the point, I believe, 0.63. Let's move on. So at the time, so let's say I will write down red marker now, and I get to put 2 over a, which is going to be with the same manner, e to the power of minus a times 2 over a, which is e to the power of minus 2, and minus 2 is 0.13, so it will be 0.87. And finally, you'll see why do I call it finally, c 4 over a equals 1 minus e to the power of minus 4. I just skip those equations in between, and I will have this really small value, right? It's something like 0.928, etc. So what I can imagine here, let's draw a graph to visualize the system response. So this is time, and this is, let's say value. It's not important, but so here we have 0, 1 over a, 2 over a, 3 over a, and 4 over a. And let's do it with red marker. At 1, we had our unit step. Let's draw it carefully. There's a unit step, and blue marker indicates our system response. So since at 4a it reaches out to almost 1, I can draw it like this. All right, so I think that's a good point. So what I can say at 1 over a, I found my value as 0.63, right? Okay, at 4a, the value is, sorry, almost there, the 0.982, and it goes like that. So I will do some definitions now, and I think you will get to understand better. So usually on these questions we will get to ask, find the time constant, find the rising time and the settling time. But what are those? Let's figure out. So there's a manner of time that increases with respect to 1 over a, 2 over a, 3 over a, and 4 over a. So 1 over a is here a constant, so we can call it the time constant. And the rise time, the TR, it means how my system, in which interval my system goes from its final values 0.1 to 0.9, between 0.1 and 0.9. So it is roughly here. All right, I think here is like kind of 2.2, but I'm not sure. It is widely called 2.2 over a. This is my rise time. And the settling time is referred as when my system reaches out at least 2% close to its final value. So 2%. And be careful, this 98.2 is inside of this 2%. So I can say my system settles down at roughly 4 over a to its 2% difference, and I can say yes, 4 over a is my settling times, let's say, formula. That's the whole case. So let's do an example to make this more understandable. We have an example here. So this is pretty easy. We are given a first order transfer function with the equation of, let's say, hs equals 50 over s plus 50. Find unit step response and time constant, rise time, and settling time. All right, let's move on. So we are given unit step response, so rs is going to be 1 over s, and hs is given, so I can say cs equals to 1 over s times 50 over s plus 50. Let's break it down by the means of partial fraction expansion, and I write down a over s plus b over s plus 50 is going to be 50 over s times s plus 50. Yeah, so a times, I will equate the denominators. A times s plus 50 plus b times s is going to be 50 because I equated the denominators. Now numerators would match. For s equals minus 50, I will have minus 50b equals 50, so b is minus 1. When s is 0, I will have 50a equals 50, and my a is 1. That's so simple. So cs is going to be 1 over s minus 1 over s plus 50. In terms of inverse Laplace, this is 1 minus e to the power of minus 50t, right? This is ct. All right, that was this simple. So I don't need to write down or draw the graph because it will be same with this graph. You can draw it by yourself. I will just find out what the time constant is, the settling time, and the rise time. So time constant, rise time, and settling time. So rise time, as we learned, it is 1 over a, and a was 50, right? 1 over 50, which is 0.2 seconds. And for TR, it was 2.2 over A, right? It's 2.2 over 50. I believe it was something like 0.54 seconds. Yeah. And settling time is 4 over A, and which corresponds to 4 over 50. I believe it was something like 0.8 seconds. Yeah. So this is how you find the response of a first order system and get the corresponding values of time constant, TR and TS. Since it looks like an easy topic of control method, but I believe it's so crucial to understand the manner, the control theory. So I hope this video was overall helpful to you. I hope you didn't get bored, and I hope to see you again in the next upcoming videos, and catch you up later, and goodbye.